Welcome back to another lesson on trigonometry. So in this video, I aim to go over the last piece of the puzzle regarding trigonometry of right angle triangles, which is finding missing angles. So our learning objective today is to be able to find missing angles of right angle triangles using trigonometry. And also, I want to get us started on some harder problems. So we'll start off with some nice real-life problems, similar to the problems to do with navigation that we've looked at, to do with ships and distances between the height of a cliff and the base of a cliff, things like that, or between the top of a cliff and the base of a cliff. And then we're going to look at some really tricky problems that will really force you to think about other concepts in maths, which are from higher tier GCSE papers. And then finally, I'm not going to go over it myself, but I will give you some videos that will really help you deepen your understanding of trigonometry if you want. It's a bit beyond what we need at this level. To start with, I'd like, so just bear in mind, I hope that you've got the sheet which was posted in Teams, or at least you've got your title in your book and you're copying things down. So I'd like us for the starter to find the missing sides x in the right angle triangles below. So A and B. And then for question 2, we've got a nice little applied question. I want you to find the length of the ladder and how far up the wall it reaches. So, the distance there up the wall. So if you pause the video, have a go, and then when you resume, we can have a look at the answers. Okay, so let's go through the answers. So for question 1, again, less is more. Let's think about labeling the triangle. So we have the hypotenuse, 28, opposite the right angle. The opposite, and then the adjacent is x. So we want to find the adjacent. We have the hypotenuse. So, we've done our labeling. Let's think about the equations. Well, our equations are Sohcahtoa. Now we have the hypotenuse and we want the adjacent, so that means we're going to use cosine. So now we've selected our equation. That's the first s in less, and the final s is then solving the equation. So I'm going to say cos of 50 degrees is equal to the adjacent x over the hypotenuse 28. Standard procedure now, I'm going to multiply both sides by 28 so I can get x on its own. On the right hand side, my 28s cancel out. On the left hand side, I've got 28 times cos 28. No, not cos 28, sorry, cos 50. My apologies. So on our calculators, we would do, let me just get this here, we would do 28 multiplied by cos 50. Again, making sure we're in degrees, not radians, giving us 17.998. So we can say that's about 17.998 centimeters, which is about 18 centimeters. So question 2, same sort of thing. Let's label our triangle. So this time x is the hypotenuse. Opposite 65, we have the opposite. Adjacent to 65, we have the final side that we haven't yet labeled is the adjacent. So let's do so we've done our labeling. Let's look at the equations. So Sohcahtoa, let's select the equation that we need. So we want the hypotenuse, we have the adjacent, so that means we're going to use cosine once again. So this time we have cos 65 degrees is equal to the adjacent over hypotenuse, so 2 over x. So it's got 2 steps this time because x is on my denominator on the right hand side. So first of all, I want to get x up to the numerator, so I'm going to multiply both sides by x, because on the right I'm dividing by x, opposite of dividing by x is timesing by x. So multiply both sides by x. Then on the right, the x's will cancel out because x over x is obviously 1. Then on the left, we just get x times cosine 65. On the right, we just get 2. So, nearly done. We can now divide both sides by cos 65. So again, we're not dividing by 65, we are dividing by the cosine of 65. And if you want to find out more about what the sort of abstract definition of cosine is, because we've defined it with right angle triangles, we defined it as the adjacent over the hypotenuse. If you want to find a more abstract definition, there'll be some videos at the end. So, but for now though, these cancel out, leaving us with x equal to 2 over cos 65 degrees. Once again, calculate this out, we get 2 divided by cos 65, which gives us 4.73 to 2, 4.73 meters to 2 decimal places, which is generally the accuracy that I want, but again, only round at the end. So, great, so hopefully all of that was okay. I'm just going to rub this off, if I may. The second one then, second part of the starter, so I labeled it as question 2, but it says question 6 here. So, second part, we have a ladder is placed on horizontal ground with its foot 2 meters from a vertical wall. The ladder makes an angle of 50 degrees with the ground. Find the length of the ladder, so that is going to be there, and how far up the wall it will reach, or it reaches. So, the length of the ladder, well, we could just think of this as a right angle triangle, the way they've drawn it. So we want the length of the ladder, which is going to be the hypotenuse. Let's label our triangle. The situation's basically a right angle triangle. So, we're modeling the situation. That's what we would call this if you were doing a physics problem. And just one aside, if you are interested in physics, this is a really common physics problem that you'll have at maybe A level, where you have a ladder against a wall and you have to work out different forces. So you'll have to work out maybe compressions in the ladder, the forces in the ladder. You'll have to work out maybe a frictional force of the floor on the ladder and the frictional force of the wall on the ladder, which I guess will go up because it will tend to go down. So you'll have to work out different things like that. Just an aside. So we want the hypotenuse, we have the adjacent, and the opposite is going to be the height of is the distance between the top of the ladder and the floor. So we want the length of the ladder first, which is the hypotenuse. So if we look at our situation, we want the hypotenuse, we have the adjacent, so that means we're going to use cosine yet again. So we have cos 50 equals the adjacent, which is 2 over the hypotenuse. So I can multiply both sides by the hypotenuse, which will cancel out hip on the right-hand side, giving me hypotenuse times cosine 50 is equal to 2. And then we can do hypotenuse is equal to 2 over cosine 50, which gives us hypotenuse equal to, So we have 2 divided by cos 50, which is just going to be about 3.11 meters. So the ladder is about 3 meters long. Let's wrap that out. And then the second bit, we want to know how far up the wall it reaches. So to do that, right, so we now want the opposite, and we have the adjacent, so that means we're going to have to use tan. So I can say tan 50 is opposite over adjacent. So if I call I'm going to call that y. Y over 2, multiply both sides by 2, we get y is equal to 2 times tan 50, which is going to be very simply 2 times tan 50. That will give us 2.38 meters, paying attention to the units. And just for the fun of it, let's plug this into Pythagoras. 2 squared plus 2.38 squared is, so if we do that, just to see if it is consistent, we get 9.6644. And if we square root that, get 3.11 to 2 decimal places, which is the height of the ladder that we worked out earlier on. So we can see that trigonometry, Sohcahtoa, is consistent. Well, Sohcahtoa is consistent with the other trigonometry we know, Pythagoras. Okay, so we're going to look at finding missing angles. So this is always fun. And this will basically conclude, this will basically finish the toolkit of trigonometry that we've looked at so far. So we can use it to solve a wide range of problems. And we start off as 90% the same as what we've already done. So it's quite straightforward. We're going to do less is more. So once again, so first of all, we label our triangle. So we look at the right angle is there. I should have drawn it on, but that is the right angle. I hope you can trust me there. Opposite the right angle is the hypotenuse always. And then opposite the angle that we've specified. So in this example, we want to find alpha. It would help if I wrote that as a question. Example 1, find alpha. Opposite is 3 centimeters, and then the adjacent would just be the side that we've not yet labeled. So we've labeled our triangle. Consider the equations. Same equations, Sohcahtoa. Sine equals opposite of hypotenuse. Cos equals adjacent over hypotenuse. Tangent equals opposite over adjacent. Right, now we've got to select the ratio or the equation that we need. Same as before. We have the hypotenuse, and we have the opposite. So it isn't a case of we have one side and we want the other. We have two sides and we want the angle. So we have the hypotenuse and we have the opposite. So let's do our ticks. Opposite hypotenuse, just opposite. We've ticked sine twice, so that means we're going to use the sine ratio. So let's now use that. So we've done these two bits. We selected it, yeah. Now let's form an equation. So our equation is going to be sine of the angle, so sine of alpha, is equal to the side which is opposite to alpha, so the one that I've drawn the first, this arrow here, so opposite 3, over the hypotenuse, which we know is 4.243. So, so we have sine alpha equals this, and then, now we're stumped. Because how do I get alpha on its own? I can't divide by sine. Sine is not a number, it's a function. So I'm just going to take a little aside just for a second. Have a think about how I could solve the equation x squared. Or I'll tell you what, different one. How could I solve the equation x squared is equal to 16? So think back to Pythagoras' theorem. Well, if I want to undo my square, what have I got to do? Well, I've got a square root, so I just do square root of both sides. So I square root, on the left it gets rid of the square, on the right I end up with the square root of 16, which is 4. Now, I know some of us are probably screaming in the comments now, it should be plus or minus 4. Yes, it should, but I'm just trying to make a point. We can see that the square, so squaring something and square rooting something are inverses. They're inverse operations. So, or inverse functions or inverse mappings. So with sine, sine is a function. It takes a number, so it'll take the number alpha, because alpha is just a number of degrees, it's a number. It'll take alpha and it will spit out this 3 over 4.243. It just maps one thing to another the same way that if I do 4 squared, that will map 4 to 16. It's the same sort of thing. And if I do the square root of 16, it takes me back to 4. So I need the inverse of sine. I need to be able to do the inverse of sine to both sides, so I'll get rid of the sine on the left, leaving me with alpha. And the inverse of sine is just, we can say arc sine if we want, but we just call it sine minus 1. And it looks like sine to the power of minus 1. It's just a weird way of writing it, but it's not a power, obviously. It's just what we call it inverse sine. And it's really easy to use. When you get to the stage sine alpha equals some stuff, on your calculator, you will press shift, sine, and equals. So I'm just going to illustrate that. So we are now at the stage where we have sine alpha equals 3 over over 4.243. I get my calculator, so make sure you're looking at the calculator now. I'm going to do 3 over 4.243, and you could just as easily do divide. I'm going to press equals. So now the right-hand side is saved in my calculator memory. I'm now going to do shift sine, and you should see sine minus 1 bracket pop up. And I'm going to do ands. Close the bracket just for completeness, and then equals. You can see we get a number, 44.995. So if I do that, we get 44.995, which is roughly 45 degrees. So, let's check that one. Yeah. Shift, sine, and yeah, that works, cos. So yeah, we get 45 degrees, roughly. And that is in fact what alpha is. Okay, because when I do shift, sine, ands, what has happened is that I've undone the sign on the left-hand side. So what we have got is, if we wanted to write it more formally, we have worked out sine inverse, so sine minus 1 or sine inverse, 3 over 4.243. That is alpha, because we've undone the sign on both sides by doing sine to the minus 1, and it gives us 45 degrees. Basically, once you get sine alpha on its own, you have it as a numerical expression, a number on the right, you just do shift sine of what you have on the right. So shift sine, whatever you have on the right. So you don't have to do it as shift sine ands. You might want to do it like this. Shift sine, you can put it all in the brackets on modern scientific calculators if you want. 4.243. You may want to do it like that, same answer. And if you want to verify this, a nice little exercise now for you would be to use the angle of 45 and see if you can find the hypotenuse given the opposite, and equally the opposite given the hypotenuse. See if you can do that. But what we're going to do now is move on to another example. So this time we want the angle theta. So once again, let's label our triangle. So right angle is there. I should have put it on earlier. So we have the hypotenuse. The opposite is unlabeled, and then we have the adjacent here. So I'm just going to be speeding up just a little bit. So we have the adjacent and we have the hypotenuse. So that means we would use cosine. So I'm going to say cosine of theta is equal to the adjacent over the hypotenuse, which is 2 over 5.385. And then to undo my cosine, I need to do cosine minus 1 of both sides. So really this is what I'm really doing. I'm really doing cosine minus 1 of both sides. If you wanted to write that in a different color, maybe. That's what I'm doing to both sides. And cos minus 1 of cos will essentially undo my cosine. It's the same thing as saying if I've got the square root of 4 squared, what's that going to be? Well, 4 squared is 16. Square root of 16 is 4. So you can see the square root and the square cancel out in the same way that cosine minus 1 or inverse cos cancels with cos. So calculator's out. We're going to do cosine minus 1, so that means shift cos, and you can either put it into your memory or you can just put it straight in. Cos minus 1, 5.385. Don't need to close the bracket, but I always do it just out of because you should have that bracket closed mathematically. So that gives us theta 68.197. So so we'll put it as 68.197 degrees or so on degrees. So theta is roughly 68.20 degrees. And once again, put it in. Check it, see if you can find the hypotenuse, roughly this value, using the adjacent and that value of theta, and the same with the hypotenuse and the adjacent. So let's have a look at question 3. So this time we have a triangle whose base is equal to its height. So before we start this question, have a think to yourself, what should theta be? What should that angle be logically? Think about it. So once you've had to think about what it should be, let's calculate it. So let's label our triangle. So we have the hypotenuse. Don't have it, but that's where it would be. The opposite would be there, and the adjacent is on the bottom of the base. There, just how it is this time. So this time we have the opposite and we have the adjacent. So we're going to need to use tan, because, Sohcahtoa, make sure you write those down. So we're going to say tan of theta is equal to opposite, which is 5, over the adjacent, which is also 5, just in this example, which gives us 1. So what we need to do now is take inverse tangent of both sides. So we need to do, essentially what we're doing is tan minus 1 of tan theta is equal to tan minus 1 of 1. So on our calculator, we're just going to do tan minus 1 of 5 over 5, which is just 1. So tan minus 1 over 1. Tan minus 1 of 1, sorry. So shift tan 1, and that gives me 45. Now, is that a sensible answer? Well, I should think it is, because 45 degrees is exactly halfway to 90. Now, because if I start here and draw a dotted line there, dotted line at the top, we can see that that angle has to be halfway between 0 and 90. It has to be 45 degrees in order for this triangle to have a base, so, for the leg of the triangle to be the same as the height of the triangle. It's the only way it makes sense. So we can see this is quite a sensible answer to be getting. So it's always good to check your answers and make sure if they're sensible, and that is a good example of that. So what I'd like you to do now is get on with exercise 1. You've got to calculate the angle marked with a letter. So look back in the video if you're unsure, give your answers to 1DP, pause the video now, have a go, and then resume when you want to go through the answers. Okay, so let's go through the answers. So for the first one, we have cos. So I'm just going to go through these quickly just to get you the answers so we can move on to some more interesting problems. So cos alpha is equal to adjacent hypotenuse. So we're going to get shift cos 9 over 13. So we get 46. So you should have 46.2 degrees for the first one. Making sure that you're showing your workings, by the way. Second one, 19. So that one you should get 19 point. So again, this is B equals 19.65 degrees. For C, you should have C is equal to, opposite hypotenuse, sine C is 11 over 18, shift sine 11 over 18. So 37.7 degrees, sorry. D, we should have sine D is opposite over hypotenuse, so we get shift sine 13.8 over 20, paying attention to the units. We should get D 43.6 degrees. And then E, you have tangent, shift tan 5.1 over 3.8. You should have E being 53.31 or 53.3 degrees to 1dp. And then lastly, cos adjacent hypotenuse, shift cos 4.6 over 9.3. So lastly, for F, you should have 60.4 degrees. So hopefully you've marked your answers and we're in agreement. Just bear in mind, in an exam, you'd need to show the full workings. Show them Sohcahtoa, show them that you label the triangle, and so on, and show them every step. Show them, you're doing the inverse functions to find the angles, just so they can't take any marks away from you if you make a little mistake. So next, we've got some real life problems. So you've basically completed, by this point now, we've worked out all the tools in our toolkit. So all that remains is to solve some real life problems and really practice with this skill. So at this stage of the video, if you want, you can pause it, have a go, or you can just watch me and maybe work at the same time as me going through them. It's completely up to you. So first real life problem is given here. So as cars drive up a ramp at a multi-story, they go up 2 meters. So when they mean up, they mean vertically up. The length of the ramp is 10 meters, and we want to find the angle between the ramp and the horizontal. So pay attention to the angle you actually want to work out. So it's not entirely clear, is it? But if you imagine now, this is the ramp. Then horizontal is obviously, your x distance. It's the flat x distance here. So the angle between the ramp and the horizontal has got to be this angle here, which I'm going to give it a name, because in maths we like to give things, we like to characterize things in maths. I'm going to call that theta. And then let's have a look at this situation. So it looks more like a trapezium than a triangle. But if I look at this 2 meters here, if I were to move that 2 meter mark, that arrow head to there, I would have 2 meters high, and I would end up with a right angle triangle. I can see that is a right angle because it's between the vertical and the horizontal. It's got to be 90 degrees. So, I just have a standard problem like before. I can label this right angle triangle. There's my hypotenuse. There is my opposite. And that is where my adjacent would be. So I can now remember so I've labeled it, equations, Sohcahtoa. I have the hypotenuse, and I have the opposite. So that means I'm going to have to use sine. So I can say sine of theta is opposite 2 over hypotenuse 10. And again, pay attention to these units, make sure they're not being mean and giving you centimeters and meters. They're not. So I get sine theta is 2 over 10, which is 0.2. We can calculate it there if we want. We don't need to. To undo the sine, I need to take inverse sine of both sides. So theta must be the inverse sine, so shift sine or sine minus 1, arc sine, whatever you want to call it, of 0.2. So on our calculator, that is going to look like shift sine 0.2, or we could indeed, you could do shift sine of 2 divided by 10. You could do this if you wanted to. As long as you're showing your workings clearly, it's okay. Don't want that though. And that gives 11.54 degrees. Great. Okay, so the second one. So in the picture, the kite is 15 meters above the girl. And that also is one thing, I really can't stress enough the importance of drawing good diagrams. You're not always going to be given these pictures, so make sure that, take a few minutes, use a ruler and a pencil, draw a good diagram. It hasn't got to be super accurate or neat, but it needs to be understandable to both you and the examiner. So, here. So we have in the picture, the kite is 15 meters above the girl. Now, I presume we don't have to take into account the height of the girl. That's just one thing here. I don't think it really matters actually. So we can say that that is 15 meters. The string is 25 meters long. Actually, doesn't matter really. 25 meters long, and we want to find the angle the string makes with the horizontal. So once again, this dotted line that I've drawn is the horizontal. So if I look at the string, it is going in a horizontal direction. If you imagine this is like an x and a y axis, it would be on the x-axis, so it would be parallel to the x-axis at least. The string is up by here, so if we look at the angle between them, I could call that angle, I don't know, alpha. Okay. And then again, it's the same sort of problem. I want to find the angle the string makes with a horizontal. Easy enough. I can just say, right, let's label it. Vertical and horizontal always at 90 degrees. Right, that is my hypotenuse. That 15 meters is my opposite, and the other side would be my adjacent. So I've got the hypotenuse, I have the opposite. So that means I can use sine. So sine of alpha is equal to opposite 15 over hypotenuse 25, which out of interest simplifies to 3/5, which is 0.6. So alpha is going to be inverse sine, taking inverse sine of both sides, sine minus 1 of 0.6, which gives me, if we work that out, shift sine 0.6 gives me 36.87 degrees to 2 decimal places. So hopefully you've had the same answers as me. I congratulate you if you did and you paused the video and had a go, that's great. Hopefully you've had the same ones. I'm going to erase my previous solutions now. So obviously go back in the video if you need to check on those. So swap it around a little bit. There you go. So a ladder is 3 meters long and is leaning against a vertical wall. Right, we've done loads of ones like this, but let's do one more just for the fun of it. So it is 3 meters long this time. Its foot is on horizontal ground 1.2 meters away from the foot of the wall. So it's talking about the base of the wall, the base of the ladder there. We don't know the height from the bottom to the top. I mean, this, by the way, is the power of trigonometry. You know, back when we only knew Pythagorean theorem. So back when we only knew Pythagorean theorem, we wouldn't have been able to work out any of these angles. So what angle does the ladder make with the wall? So we can hopefully guess by now that's going to be this angle here, you know, because we're looking at the ladder. And no, I'm being it's completely wrong. What angle does the ladder make with the wall? So the wall is this bit. So the angle between the ladder and the wall is going to be this angle, which I'm going to call theta this time. And then what angle does the ladder make with the ground? I'm going to call that alpha. So starting with theta, hypotenuse is 3. For theta, this is an interesting point. The opposite would be 1.2. So for theta, I would have the opposite and the hypotenuse, which would mean I'd have to use sine. So I could say sine theta is equal to opposite 1.2 over hypotenuse 3. Theta then, so you know, I get 12 over 30, which I can simplify. I'm just going to do it this way. Shift sine minus 1 of 1.2 over 3. So on my calculator, I've got sine theta is 1.2 over 3. To undo the sine, I need to take inverse sine of both sides. So that means I'm going to do, calculator's going to work. That means I'm going to do shift sine to get my inverse sine, and then I'm going to put in 1.2 over 3. Close bracket equals 25.578. So theta is about 25.58 degrees to 2 dp. And then if I want to get alpha, so this is now the angle ladder makes with the ground. So I'm going to erase my previous workings because otherwise it'll get a bit confusing. So angle with the ground I decided to call alpha. Right, hypotenuse was 3 meters because that's the length of the ladder. The opposite, I do not know, I don't need to know. The adjacent is given to me as 1.2 meters. So let's work this out. So I have the adjacent and I have the hypotenuse, which means I can use cosine. So I can say cosine alpha is adjacent, which is 1.2 now, because now it's alpha, it's the angle at the base. 1.2 over the hypotenuse of 3. And to undo my cosine, I just need to do cos minus 1 of both sides. So cos minus 1 on the left undoes the cosine. Cos minus 1 on the right gives me cos minus 1, 1.2 over 3, which will give me, so let me undo all that, shift cos 1.2 over 3, which gives me 66.42 degrees to 2 dp. So hopefully, and just for one thing, let's see if that works for a minute. What should the angles in the triangle add up to? You know, so I've got my theta, which was my angle between the ladder and the wall, alpha, angle between the floor and the ladder, and obviously I've got 90 degrees because it's a right angle triangle. Well, mathematically, alpha plus theta plus 90 has got to be 180 degrees because angles in a triangle add up to 180. Well, let's substitute in, see if that works. So we had alpha is 66.42, theta is 25.58, and then obviously we have the third angle 90. Let's add those up, see what we get. So it should be roughly there because, you know, 70 and 20 and everything. So it should be. So let's see how close we are. Because obviously we did round our answers, didn't we? Yeah, so we get 182, off by 2 degrees because there would be rounded the answers, I suppose. So it is approximately 180 degrees, so we can be quite happy with our answers. So, right, at this point, we have some extension. If you were happy with everything so far, then you might want to look at some of these extension problems. These are quite tricky. So the way I'd recommend you do these is, you can pause the video now, have a go, come back, go a little bit forward if you need a hint, maybe, So if you're really stuck, just go a little bit forward in the video to see some of my solution and keep trying until you can get it. Or you can just work through the problems with me if you want to. There's no harm in doing that. So this first, again, these are all GCSE problems and they're all higher tier problems as well. So they'd either be towards the end of an intermediate or they'd be somewhere either at the start or in the middle of a higher tier. So these are not easy problems, so don't be discouraged. So to start with, we have this question 1. The diagram shows a cross-section of the roof of a building with base BCD being horizontal and AC representing a vertical support. That doesn't really matter here. I mean, essentially it means that the building will look something like this. So it just basically means you've got a building like that. Well, maybe not like that, I wouldn't stand up, but you know what I mean. So it doesn't really matter. Sometimes context isn't that helpful. So we want to work out the size of the angle. So let me highlight this. We want to work out the size that the angle that the roof AD makes with the horizontal. So the roof AD is, let me highlight that again, if I may. So that's going to be not a particularly great color to use, actually. There you go, I can't really see. Now I can see better. So it's much better. So the angle AD makes with the horizontal. So that is going to be, so AD is here and the roof is going to be there. So that is, we could call that theta. So we want to work out that angle. We have another right angle triangle here on the left. So if I want, so I've got a right, I know that AC is a right angle triangle because I've got vertical and horizontal. That's 90 degrees. Okay, I know I've got right angle triangle there. If I wanted to label it, just looking at the triangle on the right, the one that I've highlighted in red, then, I've got my hypotenuse, opposite would be there, adjacent would be 10.6. Now the thing is, I only know one side. I only know the adjacent. So, I need two sides to work out an angle. So we need to think of some way to work out, so just go with that. We need some way to work out the side that I'm going to highlight in yellow, AC. How can we work out that side? Have a think. So hopefully some of you have realized that I can work out AC using the Pythagorean theorem, Pythagoras' theorem applied to the triangle ABC. If we look at the triangle ABC, we did this in the first of this video series. The sum of the squares of the smaller two sides. So if I were to draw a square there and a square there, just coming off exactly with the same width as the corresponding sides, if I added up those two areas, the areas of these squares, I would get the area of the bigger square. In the same way, if I worked out the area of the bigger square, so this one, and I took away the area of this 6.3 side square, I would get the area of this square on the right. So that was a brilliant drawing, I know. So we can use that to work out AC. So mathematically I can say AC squared, one of the shorter sides squared, plus BC squared, the other shorter side squared, is equal to 8.2. Oh, so I should write it in full first, AB squared. So I have AC squared, AC being the side that I want to work out, plus, right, BC was 6.3, so 6.3 squared is equal to 8.2 squared. So that gives me AC squared as, so just showing on my calculator, I'm going to, just to remind us what I'm doing here, I'm going to subtract 6.3 squared from both sides to leave me with AC squared on its own. So I end up with 8.2 squared minus 6.3 squared equals SD 27.55. And then, as we discussed earlier on, the inverse of squaring is square rooting. So if I want AC, I just need to work out the square root of 27.55, square root in both sides, which will give me, so I can do square root and, because that was the last thing in my calculator's memory, giving me 5.2488 and so on, which is about 5.2. In fact, actually, I'm not going to round it now. I think you'd be safe rounding it now. I think you get all the marks, but I just want to make sure that I'm consistent. I'm going to write all the figures out. So 5.2488 and 09389. I'm just going to write down, or 09389, I should say. Just going to write down all of my accuracy. So that is in meters. So we've worked out AC. So, that is 5.2488 and so on. Okay, so we have AC. Now we want to work out the angle theta. So we now have a right angle triangle, ACD, with two sides that I know, so I can work out the angle. We label the triangle, we've done that, opposite, hypotenuse adjacent. We select the equation, so we have Sohcahtoa. We write the equation even, write the equations that we know. We select the equation, so I have the opposite, I have the adjacent. So that means I need to use TOA, tangent. So I've selected my equation now. Now I just need to write the equation, solve it. So tan theta equals opposite, which is AC, over the adjacent, which is 10.6. So I can just substitute in AC. So I have 5.248809389 over 10.6. And then what I'd have to do is inverse tan of both sides. So what we could do is, just to be careful, we could do this. So I've still got that in my I've still got AC in my calculator memory. So I could just do AND divided by 10.6 equals, so 0.495. You don't need to write all display down. It's just show your workings clearly. 1706971. And then I could do inverse tan of both sides. So theta is going to be tan minus 1 of 0.4951706.971. Obviously, the calculator memory saves us a lot of work here. So I can do shift tan and, because it's still in my memory, I get 26.34 degrees 2dp. So hopefully that's not too difficult. I mean, just remember, whenever you have a right angle triangle and you want to work out an angle, well, you need two sides. So thinking on this question, don't just panic and leave it. Think to yourself, well, how can I get that unknown side? And as soon as you think of that, you should notice, well, they've given us this other triangle here as a bit of a gift to help us. So, and just one thing to bear in mind, if you really didn't like that question, if you couldn't get anywhere with it, don't worry, you've still seen a question like that now. So commit the answer to memory, and next time you're faced with a similar question, you should be fine. So, here's a mark scheme answer. So they would have accepted any answer in the range 26.1 to 26.35. So that's fine for us. But you can see the real source of the marks, strategy, an S1 mark, strategy mark. Then M1 is method marks. So you can see showing very similar workings to what we did. Root 27.55, we have that here. Tan D using the tangent ratio, AC over 10.6. So we actually wrote it down the same way. And then answer. So you can see you would have got actually 3 marks just for you. You would have had 3 marks, or actually no, you would have had. Assuming that you were accurate, by the way, assuming that you had that you were accurate in the calculations, you would have had good 4 marks just for working out the Pythagorean bit at the start. So it's very, there are a lot of marks to get. So don't ever just leave an answer blank. Do try your best. So the next one, this question is a bit different because I haven't given us a diagram. We've got to draw one ourselves. That used to be a lot more common. So Matilda rides her bike up a hill. At the bottom of the hill, Matilda was at a height of 350 meters above sea level, where she was cycling. The hill has a constant gradient and has an angle of elevation of 18 degrees. She cycles a distance of 3.2 kilometers to the top of the hill. How far above sea level is the top of the hill? Give your answer to the nearest meter. So let's draw a nice picture of this situation. So let's imagine the ground is there. There we go. At the bottom of the hill, so she's riding. Let's imagine actually that sea level is there. Really rubbish. Let's imagine that. So here we go. So let's imagine the hill. Let's imagine Matilda is there. So I'm going to draw a really excellent drawing here for Matilda because of my artistic ability. So she starts off here. So there she is 350 meters above sea level. The hill is a constant gradient and has an angle of elevation of 18 degrees. So we can imagine the hill, the angle there is 18 degrees. And what we should notice is now that means the angle between the hill and the horizontal here is also going to be 18 degrees. If you're not sure why, think back to our work on parallel lines. So you can think you've got this line here is parallel to the horizontal at the bottom, and you've got corresponding angles. Just bear that in mind. So we have 18 degrees. She cycles distance 3.2 kilometers top of the hill. So I'm going to say the top of the hill is there. So she cycles 3.2 kilometers. I'm going to use meters because I've used meters in the earlier part of the question. I want to be consistent. So I'm going to say 3,200 meters. Remember, 3.2 kilometers, 1,000 meters in the kilometer. Look back to our video on converting metric units. So I think we did a metric and imperial video. I covered that as well. So have a little look back at that if you're not sure. Again, horizontal and vertical are always at 90 degrees, so that's 90. We want to know how far above sea level is the top of the hill. So if we look at this, well, sea level is what I defined to be at the bottom here. So that is sea level. I defined that earlier on, didn't I? Because obviously 350 above is where Matilda starts. So that bottom line is sea level. I should have really done it in blue, I suppose, shouldn't I? Yeah, I should have done it in blue. No, that's really, I wouldn't want to swim in that sea. There we go, that's blue. There we go. Okay, so we can see that we want this height here, okay? So to get that, well, I could work out the height of my right angle triangle that I have formed and then add onto that 350. So it's quite straightforward. So I can see that I have formed a right angle triangle. I can see the angle there is 18. So let's label it. So the opposite is there. I do not know that, but it is something that I want to find. So 1 second. So there. The adjacent, I do not know. Don't need it. And I should have done the hypotenuse first. So the hypotenuse is there, 3,200. So we've labeled our triangle. The equations on offer are Sohcahtoa because it's a right angle triangle. And let's select which one of these we need. So we have the hypotenuse and we want the opposite. So that means I can use sine. So we've selected our equation. Now let's solve it, or let's form it first. So sine of 18 degrees, I'm given an angle this time, is equal to opposite over hypotenuse. So the opposite I'm just going to call op, and the hypotenuse is 3,200. So what I can do is multiply both sides by 3,200. So I've got 3,200 times sine 18, giving me op as times sine 18. So we get 900, and again, I'm not going to round until the end. I know that's a bit of a pain. Can I copy my display, capture? No, I can't. So I get 988.854382 meters, and then I'm going to add that to the 350. So I'm going to say total height above sea level, or total height is going to be 350 plus the opposite, which was 988.85, and so on. So I'm going to say and plus 350 gives me 1338.85 meters to 2 decimal places, and to the nearest meter that is going to be 1339 meters. So hopefully that is quite clear. So this time is a bit trickier because you have to draw it, but once you do, it's really not that difficult. So you can see here they want 1339, which is exactly what we had. There we go. And the last one, this is a really hard one now. I think this was question 10 actually on a higher tier paper. So this is not an easy question. It's not beyond any of you guys, but it's not an easy question. And you will have to remember for this question ratio, specifically dividing into a given ratio. So we did do that, not in much detail this year, but we did do it. So maybe look back on that. Okay, so A, we want to work out the area of the triangle DPC, so I'll just highlight it. So we want this, we want the area of this triangle. So area of a triangle is simply half base times height. Now, what is the height of this triangle? Well, it might not be immediately obvious, but you should notice that the perpendicular height is just going to be 4 centimeters. It's the same here because the triangle is contained exactly, well, it's not contained exactly, but it is contained exactly, I suppose, in terms of vertices within the rectangle. So the perpendicular height is 4 centimeters. So I could say that the area of triangle, that's the notation of a triangle, DPC, is equal to half times 9 times 4. You can put it in the calculator if you want, but you should know that's going to be 18. 4 over 2 is 2, times 9 is 18 units centimeters squared. Easy 2 marks. Second bit is worth 7 marks, just to let you know. So I'm going to need a little bit of space to do that. Just like move this a little bit. Let's get a bit of space here. And okay, so second bit, we want the size of angle. That little hat means I want the angle at D. So I want the angle from P to D to C. So I want this angle here essentially. Not that angle, I want this angle in here. Okay, so I'm going to label it X. I prefer using the Greek letters for the angles. I'm going to label it alpha. So looking at this, I want the size of angle PDC. So PDC. Now, right. So that 9 centimeters at the bottom. Oh, before we start, let's look at the triangle that we have. So if we look at the triangle, so I just rubbed everything out. I don't know why I did that. So if we look here, so they've asked us to work out the area of that triangle for a reason. And I think that reason is to establish that the vertical height, the perpendicular height is 4 centimeters, just to make us think of that. Now, for the base of the triangle, I know that D to C is 9 centimeters, but AP to PB is 3 to 2. So what that means is that if I, so 3 to 2, so that means that basically the top line AB is split up into 1, 2, 3, 4, 5 equal units, 2 of which are between P and B, and 3 of which are between A and P. So what that means is, well, AB is, so if I could consider it this way, I could say that AP is worth 3 units and PB is worth 2 units. All of these units individually being equal. I haven't drawn them very well, but they are all equal, these boxes. And AB, so the whole thing, the whole length of the line is 9 centimeters because it is a rectangle. So that means that the parallel sides, top and bottom, are going to be equal. So all of that is worth 9 centimeters. So at this stage, you can think about it the way I'm thinking about it with the boxes, or you might want to just use add-em, add, divide, and multiply. So I can see I've got 1, 2, 3, 4, 5 boxes, and I'm sharing out 9 centimeters equally among them. So I'm going to do 9 centimeters divided by 5, which is just going to be 1.25 centimeters. So that is what, I tell a lie actually, sorry, 1.8 centimeters. My apologies, everyone. Mathematician, there you go. So each one of these boxes is worth 1.8 centimeters. So that means that AP, which is worth 3 of these units or boxes, is going to be 1.8 times 3, which is just going to be 5.4. So I could say AP is equal to 1.8 times 3, which is 5.4 centimeters. And for completeness' sake, PB then is going to be 1.8 times 2, which is 3.6 centimeters. And if I add those up, I get 9. I get 9 centimeters. So it's sensible, okay, that's what I would expect. So now I know AP. So I can say that the adjacent, which is the same as AP because it's obviously parallel to it and it's a rectangle, or it's within a rectangle, I can say that AP is 5.4 centimeters. And then if I let's clean up this diagram a little bit because it's a bit messy now. So let's clean it up. So we have dotted lines. So we have the vertical height of the triangle. There we have AP, which is the same as this here. On the bottom was 5.4 centimeters. We know this vertical height is 4 centimeters, and we know that we don't know anything else. We just want to work out the angle alpha PDC. So now we have this triangle here, which I will just highlight briefly in yellow. So here we go. Oh, that's not yellow. There we go. So we have this triangle here. We have the hypotenuse there, the opposite, and the adjacent. So what we need to do to work out PDC is first label it. So we've labeled it. The equations, Sohcahtoa. So now we need to select which one we need to use. So we know the opposite and we know the adjacent now. So that means we can use TOA or tangent. So I can say tan alpha is equal to opposite. So 4 over the adjacent 5.4. And then I can work out alpha by taking inverse tan of both sides. So alpha is inverse tan of 4 over 5.4, which in a modern scientific calculator we can do very easily. So we do shift tan 4 over 5.4 equals 36.53 degrees. And let's just check what the mark scheme says. So 36.5 and so on. So you will accept 36.5. 36.53 is fine. And you can see overall strategy, use of ratio. I'll make this a bit bigger. Use of ratio in trigonometry, which is what we did. 9 divided by 1.8. And you can see that every one of these steps that I've written is worth a mark, basically. This is 7 marks for PDC. So don't throw marks away, make sure you show your work-ins. So that basically concludes it. We've looked at trigonometry for right angle triangles. We've worked out missing sides, missing angles, and some real life problems, like the GCSE problems. If you've managed to understand everything we've done, you've worked hard on it, and you've done the My Maths and Maths, well, I'm going to be setting My Maths and Maths Watch on this as well, then you'll have a really thorough grounding in this subject. And if you are really interested, in trigonometry and where sine, cos, and tan actually come from, then what you can do is look at the videos that I put at the end of the sheet on Teams, on Khan Academy on the unit circle. It's much more advanced than we need at this level, and indeed even at GCSE, but it is interesting, and it gives you a bit more of a mathematical sense for these things. So, thank you so much for your attention. If there are any problems, please let me know on Teams.